This video is brought to you by Hygromo Chalk. Use code TPSA 10% off to get a discount. So now just to go over the idea of limits in several real variables. They behave exactly as you would expect them to, but just to give it a bit of formality. We have x in Rd and f mapping x to Rb. If p is a limit point of x and q is in Rb, we say that q is the limit of f of x as x tends to p, written this way. If for any epsilon greater than 0, we can find a delta greater than 0 such that when f of x and the limit are within an epsilon are within an epsilon of the other. This occurs when the distance between x and p, the limit point, is non-zero and is less than delta. And you can check limits for multivariable functions back to Rb very easily, because all you need to do actually consider here is completely equivalent to look at the limit as of the function. You see q is the limit, q vector q is the limit. If you just look at the, if q doesn't Rb, so you just look at the b components of q and the b components of f, and just check each of those limits individually. So that just doesn't take much more than vector calc. Then we have this theorem which just says essentially if the properties that we expect, so that the limits of f and g both exist and both of these map to R, p the limit point of x, then you can add, subtract, multiply, and divide exactly as you'd expect. For dividing, you need to make sure that g is non-zero on the whole domain and that its limit is also non-zero. But yeah, the limit just, we can exchange it with the sum minus product and quotient. And then finally, this theorem, which relates back continuity. A lot of people will come at continuity from the definition, but we can act like this will be the definition of continuity. But we can use it as a theorem because we've defined continuity in terms of balls. So here we have if x is a subset of Rd and f maps x to Rb, p is in x and is a limit point, then we can say that f is continuous at p if and only if the limit as x goes to p is in fact f evaluated at p. And I don't think this needs a diagram because this is exactly how limits are taught in calculus.